Okay, it's just a coincidence, but our next speaker has been my boss for the last 3 years.
Has been?
Still, and Professor Helmut Ritsch from University of Innsbruck, and he will tell us, I guess, about dipole-dipole interactions in ordered atomic arrays.
Yeah, this was fun. Well, thanks anyway, and good morning, everybody. I mean, I was asked to spontaneously jump in here, which I am really glad to do, and present some of the results which I presented recently. So not everything might exactly fit to this conference, but I'm fine. But before I start and before Ineke leaves, I have to say that I have to thank this network. It was really a great pleasure. And I've been in many of these networks, and she was the best administrator of any of the networks. And so the one who gives you the least nonsense things to do during the whole stuff, you only have to do the essential stuff. And also Florian and Yeshval were really trying hard to do all the nonsense stuff for the other PIs in the network. So thanks a lot. That was really great. And so this could continue for a long time and for many networks. Okay, so what I'm talking, there is no pointer. Oh, there is a pointer.
Yeah, but don't use it.
But it doesn't work. Yeah.
But there is a pointer in the laptop if you like. Laser pointer.
There is a laser pointer in the laptop, so I'm not really used to do this, but pointer options, laser pointer. Okay, now you can see this. Okay, so now this is different from the previous two talks. It's a theory talk, so it comes totally from the other side. We've seen fantastic experiments and also setups where one can reduce the real complexity to the world to very small measurements and systems, which can almost be fully analytically treated. Yeah, and here I really want to go into the other direction. Before, I have to say, I mean, you can see from the color of my hair that I don't do most of the work myself. So there was a PhD with our postdoc Raphael Holzinger, there was Anna, and a few other people in my group, mainly in this, and I had a very strong correlation with Maria Morena Cardona. She's now in Barcelona, Claudio Guenes, and then there's Stefan Ostermann and Susanne Jelin in Harvard, who also contributed at least to the later part of this work. But anyway, so we are theorists and we like to play sort of Lego. So it's mainly we start from Gedanken experiments, and what we actually only have available is two-level atoms. Let's say we have the minimal Lego version, so all we have is a two-level atom, but we can place them in any distance to each other, and this atom has a sort of a dipole moment which induces a radiative transition. And we can, the other thing we have is lasers and light sources. And it's amazing that having only this, you can do really a lot of interesting Gedanken devices, which nowadays, and as we've seen in the first talk, become real devices in some sense. What you can see is actually, if you just put the line of these dipoles very close to each other, you can create an almost perfect waveguide. If you form this line into a ring, you can build optical resonators of IQ. If you put some gain, you get a laser, you can have beam splitters and other optical elements, which even are realized nowadays with just lines. I mean, there's been some nice work in Durham as well on this. And you can build antennas and light harvesting devices, which for some reason mimic sort of the things that nature already invented, or you can even create non-classical sources. So all you have is two-level atoms, which you place somewhere, and some light sources. Okay, the basic principle, which I will repeat here because I think that not everybody knows it, but most people will know it here. I slipped this in. So if you have a single two-level atom, it's rather boring. You can excite it, and at some point it will spontaneously decay to the ground state, so the famous quantum jump, and one photon will be emitted. And basically we can calculate the rate from the dipole moment, and it can be done in vacuum or in some thermal background where there's some extra enhancement, stimulated emission, either by vacuum fluctuations or by real fluctuations. Maybe even dark matter can stimulate here. I'm not sure if there is any serious numbers on this. But anyway, we know that if we change the environment, then the whole thing is already modified. So the simplest case is putting two mirrors around my atom, and I later won't use this anymore. This is more as a Gedankenexperiment. We get sort of this famous enhancement or Purcell effect, that the vacuum fluctuations are redistributed in space. So you can enhance or decrease the vacuum fluctuations around your atom, and in this way get a faster or slower decay. So here we have some comparisons. So the orange line is sort of a certain coupling strength to the vacuum compared sort of to the free space in blue. We see that you can enhance it. Of course, you cannot enhance it arbitrarily fast, because once this stimulation is bigger than the lifetime, faster than the lifetime of your photon in the cavity, you get reabsorption. So there is sort of in principle some enhancement factor which is limited sort of by your cavity line widths. Anyways, this is a well-known and experimentally well-proven and used in many cases type of way to modify sort of spontaneous decay. The other thing is we have two atoms, basically we have the same. So the second atom, in some sense, is also a resonator. So if we put them close together, the atoms interact, and now we have basically the same effect. There is not only a decay into free space, but the energy can be also transferred from one atom to the other one. And even there can be superpositions where the decay is not individual, but collective. So surprisingly, from a theoretical point of view, there is only one complex number to describe this process. So the real part is energy shifts, and the imaginary part is sort of enhanced or suppressed spontaneous emission rates. So again, if we have two atoms, in theory, we can go to a different basis. We have the doubly excited state on top, and we have sort of the two possible single excited state in the middle, and we form sort of the symmetric and antisymmetric superposition and see that one of those states lives very long, of the antisymmetric one, and the symmetric one has a very short lifetime. So we get a very similar behavior, sort of compared to as with the cavity. So we can enhance the decay. Let's see for the red curve beyond sort of the single atom decay. And if they're too close, if this enhancement is bigger than the lifetime, we get again these oscillations. The difference with the atom is that the atom has a limited amount of taking up energy, so it's not a harmonic oscillator. So we also have an anti-Purcell effect, and this is the subradiance. So the atom can also provide the opposite of a Purcell effect and really prevent sort of the decay of this coupled system and create very long-lived states. And of course, from the point of electrodynamics, it's very simple. If you split the energy between the two atoms and we bring them closer and closer, if there is a plus sign in between, what we finally get is just a dipole which is twice as big. So this dipole has twice the dipole moment. If we have a minus sign between this energy splitting, what we get is a quadrupole, and this quadrupole gets very, very tiny. So it can be orders of magnitude smaller, and it's a quadrupole, and that's why we don't see much radiation coming out compared to the superradiance case. So left is here we have the super radiant case, and this is the subradiant case. And basically this is the whole physics behind the rest of what I will be talking about. So again, two particles, we can have we can have a single dipole if only one is excited and the other one is far away. We can have the symmetric dipole, which is stronger, and the antisymmetric quadrupole, which is much, much weaker. Of course, if we go on, we have many of these atoms, then each atom interacts with the other one, and sort of this is a pairwise interaction, so we can sort of eliminate all the vacuum modes from our model. So what finally stays is just a collection of interacting dipoles with frequency shifts. And what we do in quantum optics, we open system, we write down the corresponding master equation with the Liouvillean, and we see sort of that the real part of this interaction ends up in the unitary Hamiltonian, and the incoherent part ends up in the Liouvillean. So in that sense, the model is fairly simple, and we don't have to care about all the vacuum modes in this system. Of course, practically, from theory point of view, it gets complicated because, as we all know, the Hilbert space of the system grows exponentially. So we can only treat a finite number of these particles numerically, and the analytical approaches are also limited because the interaction usually is sort of not linear, but has cosine and sine terms and all kind of things. And there's been a lot of work of this 50 years ago, and many results or even experiments were done, mainly on superradiance, but which has decayed and recently got some kind of renaissance. So now let's build devices in our mind, our Gedanken devices made out of these dipoles. And the first thing is just have a dense chain of atoms with a distance smaller than the wavelength. Actually, you have to be smaller than half of the wavelengths. And then you can show actually that the wave vector you can create inside this chain is bigger than the free space photon wave vector. So the photon cannot escape as long as it's in the chain. So the only way it can escape is at the end. So we put some excitation in the center, which would, for a single atom, decay at 1 gamma. We see that this chain will guide it towards the end, and some of the excitation will stay for a very long time. So even at 25 gammas, we still have some probability of this photon coming out very, very much later. And if you analyze it, you find that basically the longest lifetime scales with the cube of this number of atoms. So if you have 10 atoms, you get 1,000 times longer lifetime than you would have from a single atom in the best case. And by changing length and distance and so on of this, you can tailor the emission profile and the line, which you can also a bit understand. Sort of one n comes from the time the excitation travels back and forth, and the n squared comes from the angle getting narrower and narrower. So the emission angle, so that the vacuum fluctuations which are coupled to the emission, they shrink. So this angle goes with 1 over n. So in total, we get the n cubed. And of course, one immediately thinks, okay, if we have this n cubed, can we do sort of better? And as we see, it's actually the ends which make the loss. So now we need a chain without ends, and this is a ring or a polygon. So we can do the same calculations now for polygons. Theorists love it even more because there is easier to do an analytic treatment. We can get Bloch waves and eigenstates and everything analytically. And indeed, we can show that for any given distance, if we increase the number of particles in this ring, we see that the polygon really has an exponential lifetime enhancement, whereas the chain has sort of this 1 over arc n cubed dependence. So large enough ensembles, the ring is much better than a chain. And what it actually means, if we look at the field distribution, we see that a ring which is actually only a fraction of a wavelength in size can still store an excitation for very, very long time. So these dark states, they have very complex but concentrated fields, but also the bright states have a field intensity which is localized sort of close to the ring, so at sub-wavelength distance. So in some sense, we can keep a lot of the intensity close to this ring. Of course, there is the transverse dipole, which radiates for these bright states. Anyway, it's not so easy to do it with atoms, placing atoms at, let's say, 1/10 of a wavelength in a nice ring. But it turns out, if you look around, nature has done it. So in light harvesting structures in nature, you find always, in many cases, you find rings. It's one of the most common molecules which are parts. And so this gives us some idea. Then we use this idea even for sort of an antenna. So we have such of a ring, and now can we use this ring to catch a photon? And in order to make a model, our detector is again a 2-level atom. So we don't have much more to build. So we put this now as a first case in the center of this ring. And we do only a small cheat. So here we assume that the center atom has an extra decay channel. So in order to find out what's the real probability of catching this photon which comes along, the center atom is not a 2-level atom. It has some other energy channel which dissipates the energy into a third target state. And we can just ask at the end sort of how much of the incoming energy, how much of the field ends up in this sort of state that we want to catch the photon in. And there was a bit of a surprise. So when Mariona tried to optimize these probabilities, she found some rather funny thing is that if we have a small ring, so this is lambda over t, t means, so if sort of the dimension of the ring is, let's say, 1/10 or 1/20 of the wavelengths, then there is a very strange optimum of this efficiency for exactly a ring of 9 atoms. So this was a bit of a surprise. There are other optima for larger rings, but for these very tiny rings, we have the optimum at 9. And we can also now change the properties of the impurity a bit by saying, okay, we have a better or worse impurity, or we change its frequency. Then this 9 can sometimes be also 8 or 10, but mostly it's of the same order of 9, and 9 is sort of the most common thing. And of course, the more interesting thing is that in nature, almost all rings have 9 atoms. So 9 is the common size of these rings. And the question is, what's going on here? And if we look a bit closer at the dark states, we see that this 9 ring with the center has the most dark state. So it has a state which is almost not radiative, but still coupled to the outside field a bit. And if we look a bit closer to this 9th state, we see that this 9th state is quite special because most of its occupation is in the center. So what we actually have, we have this ring, which is a resonator, and there is an anti-dipole in the center, which sort of kills the re-emission and gets all the energy out. So this is sort of one of the technical reasons why this 9 is good. And of course, we can also ask what is the physics behind this 9? And it was a bit puzzling because for the first moment, we couldn't really figure out what's going on, until you see it must be geometry. So there is no other chance. We have this big dipole in the center, and we have sort of this ring of dipoles oscillating in the other direction when we get sort of plane wave illumination of the thing. And if it's sub-wavelengths, anything is plane wave. So whatever light comes in, it's like plane wave light for this very tiny thing in the sense. And one sees that at these small distances, the main interaction is 1 over distance cubed. And there is this strange relation that 9 over this over r cubed is just the sum over the interaction between all the ring atoms. So only for 9, everything gets the same light shift. And this is essential to form this very dark state in this kind of model. You can also change the illumination to broadband, and surprisingly enough, for typical parameters, still even for not coherent but broadband illumination, we get this enhancement at 9. And then people always ask, is it quantum or not? And then in theory, it's a bit easier to answer than maybe in the experiment, because we can just calculate the mean field model in green and compare it to different levels of quantum calculation. And we see that for most of the sizes, it's a classical antenna effect. Yeah. But if you really want to show and you go beyond the optimum size, yeah, you see that there is some quantum enhancement compared to the classical model. So in some sense, there could be something quantum in there, but of course, the optimum of the quantum and the classical models, they are very close. Anyway, I think nature doesn't care really if it's quantum or not, if it works. Yeah. Okay, there's been experiments. I mean, we know there is this dipole-dipole interaction experiments, and people before our calculations, they tried even to do this with DNA origami. So there is a way to create sort of regular configurations of molecular dipole or molecular chlorophylls using DNA origami. And the people were testing this, but unfortunately, they always went up to only 6. So I talked to them and they were saying, okay, they didn't think about it, and they will rethink of maybe they can also use the 9 one, and up to 6, you don't see a lot. Basically, you see that each fluorophore just adds the same amount. So there is none of these enhancement effects visible, but maybe someday somebody can look at this more deeply. Next thing is, okay, we have now an antenna, but now we can also create, instead of an antenna, sort of a transmission line. So we have an emitter and an antenna, and we can compare the case of sort of 2 freely spaced particles and 2 particles which are in such a ring chain. Yeah. Why would we do this? On the one hand, also nature has this kind of more complex structures, at least in some of the bacteria, where there is a lot of these 9 rings randomly or even not randomly distributed, and somewhere in the center there is a more complex structure which digests this energy. Again, we can reduce it and calculate radiant and subradiant eigenmodes, and we already see that this bacterial structure is also working like a parabolic mirror or some sense. So it's really just a focusing structure at, I mean, the whole thing is still sub-wavelengths, but an incoming sort of plane wave is very strongly focused at some point here. And also, whereas sort of in the non-radiating modes, we see that there are much more delocalized excitations going on. So how about transport? Starting with the simplest case is 2 rings. We put sort of, and we see that the dark modes really are like optical resonators. So in the dark modes, the 2 rings are like mirrors concentrating the light in between the close points. And whereas the bright modes are just like 2, on the lower side, they're just like 2 bigger dipoles acting together. Yeah. Now, what is the dynamics here? If we put such ring and we put sort of an excitation into one of the less radiative modes, what we see actually is that it's getting slowly but very efficiently transferred to neighboring modes. If you take more of them, the same thing happens. So finally, after a little bit of complex dynamics, it will end up at the other mode. And here on the left side, we compare sort of the ring transmission compared to just two atoms sitting there without the rings, where everything goes basically into the free space radiation immediately without any efficient exchange. I can also show that this sort of transfer goes, the better the larger the wave packet is that we have in one of these rings. So it's really a sort of collective effect which enhances also the transport between the rings. It's not really the absorption, it's just the transport, because this goes back and forth for a long time. We can add the emitter and sender atom into the ring, and it's not a big surprise, sort of. It works better, but the surprise again is this is now for 8. It works, but not as good. But again, it works best for 9. And this is just a picture of such ring structures in biological systems. And that what we want to mimic here in a simple case. So on the we put 2 of these rings we consider to be senders and receivers of, let's say, 1 qubit, one would nowadays say, but let's say 1 single excitation, and we see how this is transferred between the different rings. Again, we see that the 9 ring has again some not very strong, but a little bit of advantages compared to sort of 7 and 6 rings. If the ring number is too small, then the whole effect is vanishing largely. Let's see what I have now here. That's the other thing is what makes the 9 a bit more special again is that if you change the properties of the absorber, so you say that the absorbing system can digest very slow or very fast. What is the best? And it seems more or less the best is if the digestion rate sort of fits sort of the decay rates of the other atoms, but this will usually not be the case. This other transition might be different and just have a slower or faster decay rate by 1 or 2 orders of magnitude. And we see that again for the 9 ring, this does not change this efficiency, whereas for smaller numbers and bigger numbers, the range where this transfer from sort of the sender state to the absorber state works well is biggest around n equal 9 again. Why is this the case? And then especially Raphael and with Susanne Jelin, they were studying this in a bit more detail and looking at the eigenstates of all of this. And what appears again is this famous edge state picture. So what one sees if one does these calculations, that in this system, and especially if they become small, we get this delocalized edge state, where the excitation is concentrated at the ends of this chain, but it's sort of energetically different from all of the other states, radiating states, or even not so much radiating states, which then facilitates this very efficient transfer from one edge to the other edge of this whole thing. It's a bit like a stirrup process that we saw today in a more complex environment. So actually the energy is never really in between, but it has to go through. And this makes this very high transfer efficiency. One can look at different geometries like chains and lattice geometries, and again see that depending on the geometry and the ring size, the efficiency of this transfer is changing. But what is also quite interesting is that the robustness of the transport, if you now start disordering, you say, okay, my rings are not perfect, they have slightly different size and they slightly different position. Seems again that for the 9 ring, which is on the on sort of this upper is the solid line. Yeah, there is sort of the most robustness of against transport disorder for this transport. There have been experiments by Nick van Hulst, and they were studying this transport in real chains, and it was a very difficult experiment because once they put the excitation in at the center, yeah, and looked at the fluorescence at the outside board, they didn't see almost any fluorescence. And actually, this is exactly what the system wants. I mean, the system doesn't want to give back the energy. So the experiment was tough. They saw this diffusion, but it was not so easy. But he's recently got an ESC grant to do this again, maybe in a more detailed way. I think this I didn't want to show. Yeah, so this was one thing. So we're building antennas and transport systems, but could we do something more? Yeah, and the thing is, can we operate this whole device in reverse? So we have a very good antenna which puts energy into a center atom, but if we turn the thing around and say the center atom is not an absorber but a gain, yeah, what do we get? So now again we have a ring, and in the center we put an atom which now has an incoherent pump rate. We can debate. For theorists, it's easy. It's one more constant, an inverse gamma. But of course, in the model, you need more levels and a bit more tricky things to do it. But anyway, is there light coming out, and what are the properties of light coming out? And if one sees, let's say, if we turn on this pump at the center, we see that indeed, after a certain amount of time, the ground state of the whole system is not populated, it is less populated, and there is the first and second excited states are populated, and at the same time, sort of photons come out of this system. Yeah, and we can change then this is in time for a given pump rate. If we increase the pump rate, we see that at a certain point, the ground state actually is not occupied at all, and we get something which is sort of a general type of inversion in this system. And if we look at the radiated light, and this is a calculation by Raphael Holzinger in my group, you see that actually the stationary field distribution almost looks like a ring laser. So we get a light field around this ring, which of course it's so small, there's not much other choice, but it's spatially perfectly coherent. So we get a spatially coherent emitter here, but the nice thing is that also it's not only spatially coherent, but also temporally coherent. So this excited symmetric state turns out to really play the role of a miniature resonator, and if we have a resonator and a gain, we have something like a laser. So we can build a coherent light source, and actually if we optimize the pumping a bit, we see actually that the line width of the emitted light can be even narrower than the line width of a single atom emitting, whereas the number of photons emitted strongly grows with respect to the scattering from a single atom. So the G2 function gets, I mean, yeah, so this in many respects is like a laser and actually has the size of 1/100th of a wavelength or even smaller. Still, it's a theoretical laser. Of course, you can also go to molecules, and I mean, for theorists, the molecule is just a two-level atom and a harmonic oscillator, so beware. There are more complicated molecules in real life, I agree. But to make it a bit more realistic, we shifted the two oscillators, so we have sort of some kind of overlap of functions. And what we actually see is the whole system even works better if we have these vibrational degrees of freedom, because then the pumping can be optimized better, so we can pump on some vibrational levels and emit on other vibrational levels. And we can see that the lasing properties basically stay the same. Again, we get now a nicer threshold, and the G2 function gets to 1. So this kind of molecular ring with the corresponding pumping even more resembles the typical laser than the other thing. I don't know, is there
questions? So you have 5 minutes.
Okay, that's perfect. So this was all linear, but of course the two-level atom is intrinsically nonlinear. And so can we also make use of the nonlinearity? And this can be done if we, again, just take a chain and we illuminate it now with coherent light of the correct frequency and look what's coming out. Yeah? And one of sort of the easiest cases is you send a coherent beam along this axis and you look transversely. And then you can address either the frequency of a dark resonance or a bright resonance. And again, and then you see actually that this is actually quite an interesting light source. Because of the nonlinearity, you don't usually reach the 2 excitation manifold. So the system blocks sort of 2 excitations in the system. And if you look at the transverse direction where the incoming light is not present, we get a very, very small G2 function. So the G2 function is close to 0.01 for some, I think, example of this was 10 atoms in a line, coherently illuminated. And then one could always say, okay, that is sort of trivial, because even if I take 1 atom and I illuminate it and look to the side, the G2 function is even 0. Yeah? But what is the difference? The difference is that you can also use you can also address the superradiance state, so you get a lot more photons out. So what is the difference if you make this chain longer and longer and you illuminate correctly and you target the symmetric state, you get sort of an n times the spontaneous emission rate of a single photon, and still to a large extent keep the G2 function not as small as one would really hope for, not too small sizes, but also due to the length of the chain, the emission gets transversely focused. So you get more photons into a small solid angle, more single photons. So in some sense, you can also build a nonlinear single photon source just with a single chain if you have proper orientation of the dipoles and proper pumping. And okay, the last -5 minutes. The question is, it's a bit hard to do this with real molecules, atoms, or other stuff, but sort of in the superconducting waveguide people, they can place their emitters at any distance of a very small fraction of wavelengths, or even use a waveguide and put them at 1 wavelength distance. And what we noticed is that this could already simulate a ring. If we place our qubits at the integer wavelength distance, it's a bit like a ring, because the interaction of each one with each one is the same because of the periodicity of the waveguide. And so we can find these collective dark states that we found in the rings also in this infinite waveguide chain. And also other stories, we can also see that if we sort of put 1 absorber into this ring, that the transmission goes to 0, and basically all the energy ends up in one of these emitters. So the antenna idea also works. This Q-to-ring antenna can be also stretched into a linear thing if we replace the 3D vacuum with a 1D waveguide type of vacuum. So it's a bit of a trick, because these qubits don't emit into free space anyway, so they are dark in some sense. So you use the waveguides to destroy their darkness, and then you construct the dark state to recreate the darkness. So you can have sort of artificial subradiant states. and use them for transmission or absorption. Finally, some kind of advertisements. So all of these calculations are fairly easily and are done with two Julia packets, which we developed, and everybody, I'm happy to use. Everybody is invited to use. So all of these things only need a fairly small amount of code, because the model is like a Lego. And so you don't only need a finite number of elements to simulate all of this. And this, I think, brings me already to the end. And yeah, saying that from a theory point of view, Gedanken experiments, you don't need much to make interesting optical elements. Just a few atomic dipoles, placing them at the right positions with the right properties. Thank you.
Yeah, questions. It's about calculations, because you mentioned that for example, to simple ring of 10 atoms, you can get full quantum calculation, I think.
I'm sorry, can you speak a bit louder?
Okay, for 1 or 2, maybe 3 rings of 9 atoms, you can do the full quantum calculation.
Yeah.
It's possible, but you showed us the systems with many rings, like 16, something like this. How can we perform calculations?
Yeah, so this is, you're right. I mean, I mentioned at the beginning, the good thing is that we don't need the full Hilbert space. So you can cut off at any number of excitations. And so in most of these cases, we're staying with few excitations in the system. And so the number of equations only grows maybe quadratically with the number of atoms or third power if we have sort of a limit to 2 or 3 excitations. Of course, we have to check, and you see that due to the nonlinearity in the system, higher excitations are extremely rare. I think this is also one of the biologists from Israel told us, that is sort of what nature even cares more, is that the things are not destroyed by too much light. So it has to be efficient at low light, but it should be very bad at higher light levels, otherwise you destroy the system. So this nonlinearity is helpful, and the nonlinearity helps us in the calculations. You're right. If you have the 88 dipoles of the full LH1 molecule, no way to do the full quantum.
So you essentially truncate the space by low levels of
Yeah, you truncate the Hilbert space at number excitation, or the alternative approach is the called cumulant approach. So we have this other package. No, it's not mentioned here. There is a cumulant package where you can make the sort of mean field calculations, and then the next, the next order and the third order. And in this way, you can treat very large systems in an expansion of 1 over the system over the size. Yeah, but it's definitely not that easy. Yeah?
One might be another question. How well is this cumulant results with cumulant approach match the results with truncated Hilbert space?
Yeah, I think this is that's what we compare, and in the very weak excitation limit, mean field is almost exact, but then it gets worse. And at the moment, I have one master student trying to see how the orders of the cumulant expansion for the rings converge, and it seems to be surprising much better than I thought. But this could be that the system sizes are not really that big, but it seems that that second order is enough to show most of these, for instance, quantum enhancement effects you already see in second order. You don't need the full Hilbert space.
Because you in principle can at any level of excitation to the system.
No, the cumulance is good for a lot of excitations. Yeah, it's the opposite limit. Yeah.
We have time for one small question.
In your introduction, you showed that the quadrupole can be generated as a sub-radiant superposition of two dipoles. I never thought about this before. I find it interesting. Is it really a pure quadrupole pattern, or is it also higher order multipoles?
I think if it's arbitrarily close, it gets a pure, but it's not in a practice. It's not. Yeah. In practice, at any finite distance, there is still a little bit of dipole contribution, dominant quadrupole contribution, and probably anything else. Yeah.
Do you think it could be extrapolated in more general terms to higher order multipoles, so saying that combining two quadrupoles would produce an octupole or something?
I guess so, but this is a guess.
Okay, very
Quick follow-up to this question. I didn't understand your slide there because you showed it one time two dipoles like this and one time one on top of the other, but I don't think that's what you mean, is it?
I don't know. It should never be on top. I mean, there is, of course, maybe, yeah. It makes a difference. I mean, if the two dipoles sort of are parallel oriented, then sort of they maybe have sort of repulsive interactions if they come close. If they're this way, they have attractive interactions. And it changes. I mean, I have a slide on the angle and on the distance. So the quadrupole I showed was for parallel, but there is also a similar quadrupole appearing for sort of if they are facing each other. That's not too much different. It's just that the energy levels are, in this case, the dark states have lower energy, and in the other state, the dark states have higher energy. And for molecules, there is this Kasha rule or whatever, makes a lot of difference. So what are the aggregates called J aggregates and the other sort of aggregates, and they are precisely these two cases, yeah. And in one case, you can populate the dark states, and in the other one, no way. Yeah. But if there is what happens in the intermediate case, let's say the distance vector is not orthogonal or parallel to the dipoles, you can calculate, but I don't know what kind of field configuration this would mean. Probably you have to decompose into the two components, and then you get an interference of the two. I don't know. Yeah.
Okay. Thank you very much.